Apologies, I'm running a little bit late today. It's going to take me 1 minute. I'm going to be setting up a new setup here. So give me just 1 second.
Recording in progress.
All right, so turn this down. Okay. Okay, I'm trying to figure out how to. This one. Does anybody have a piece of paper? I realized I don't have any. Okay. Let's do we can make that bigger. Okay, this is going to be a little bit interesting. I wanted to go over a few concepts, which were not so clear or seem to be confusion still in the first exam. So one of those concepts is a floating node and then the voltage difference. So you can see this. Okay, so here's my circuit. I'm going to have a battery. Mute. Okay, so I'm going to hook up the battery. It's going to be in the positive side, and then the negative will be in the negative. So the positive side of the battery, maybe. So on this, you can see that I'm going to hook up the positive side over here. There we go. Okay, so positive side of the battery is connected here. Goes into this first resistor. And on that, you can see that it is, maybe not, there we go. It's connected all in that line. And then I just did a jumper wire to the next line. And then that's another jumper wire to the next resistor. And then that resistor goes to the ground portion. And then this resistor goes to another resistor and then to ground. So to draw this, this is going to look like this. I have my battery. And then I have that blue wire that goes to the resistor on the top, which is this one. Call it R1. And then I have additional wires here. And there was 3 of them that then go to this one, which goes to ground. And this one, which goes over. And then another one that goes to ground. So this is my circuit here that is exactly the same. So my point that I want to make is all of these little jumper wires, if I was to measure each one, what should I expect there? 0 voltage difference. So it should be the same at every single little wire. So just wanted to go through this exercise just because this seemed to be a concept still a little bit lacking. So we're going to physically do this, sorry. Put these on. Okay, so on this, I've hooked up the black wire of the multimeter to the negative. Here we go again. Which one? I think. Yeah, it's not going to focus. Yeah, it won't focus on that one. So, all right, so I'm looking at the node right before this. So what should I measure here if I hooked it up to a 9-volt battery? Yeah. Sorry. All right, so this node here that's right above the battery, this is 9 volts. I should measure about 9 volts there, right? So on this circuit, that is going to be where I literally just took it in. And so there's a wire in between there, that blue wire. And I do measure, you know, around 9 volts. So that should be what I expect. So notice that there's still a wire in between there, just like there's a wire there. So if I was to measure here, it would still be 9 volts, correct? Okay. So that's the concept that I want you to think about, is the physical part, which is there's actually physical wires, but the location may be different, but the voltage is still the same. Okay. All right. So then if I measure now over here, I'm going to have a voltage drop, right, across that resistor. So now I'm measuring 298 millivolts. So on the circuit diagram, that means that I'm at this location right after the resistor, and that's 298 millivolts. So I should also measure 298 millivolts here, right? And here, right before this resistor, right before that resistor. So if I put this on, I lost my negative connection. So now at a different place in that wire, I should still be measuring what here? 298. So there's 298 millivolts. And I shouldn't be measuring it along that same wire. This is again a different location, but it's still 298 millivolts. And then across here, I should be measuring on this side of the resistor. I still measure 298 millivolts. On this part of the resistor, I should still be measuring 298. Okay, so I want that concept to kind of be in there, that even along each wire, all along that wire is the same voltage. So that seemed to be a little bit of a confusion still. I thought maybe this demo would help to be like, oh, that makes more sense. You know, physical location may be different, but the voltage will be the same along each of those, because a wire is the same voltage value wherever that wire is. Okay. All right. The other concept is that if I have now a floating wire, so now if I take that off, my circuit is going to look like this, and I have a voltage source that goes to ground, and now a resistor that is just floating there. What will I measure here? Should measure 9 volts. Why? Correct. Yep. So it should still be just 9 volts. So as I measure here, I can grab that. You see that, yes, there's no volt or no current going through there, which means no voltage across that resistor. Yes. You have to have a closed loop in order for current to go through it. So, yep. So I have to have some way of connecting this, you know, to ground, but because it's open and just floating there, there's still a difference in voltage between that location and ground, right? So between this location and ground, where it's still open in air, there's still a voltage difference there. And so that's why we're measuring, 9.17 volts across there. But that is the same between those. Does that make sense? Okay. So this concept didn't seem to be solidified. So think about this, make sure you do understand that. So now, if you're looking at, when we draw, like, you can draw something like this, where it's open, but there's no current going through these dangling wires. But this means that I would put the red probe across this to ground. And I'm going to measure the the voltage across this resistance at this location here. That is the same as I've hooked now these dangling wires, and I hook it across that last resistor there, which is there. And I lost something. Oh, I'm not hooked up. I'm like, wait a minute, it's 0 volts. Okay, hooking back that resistor in there. And so across this is my dangling wire off of it, and then that's my black one on the end. So it's just like this with the red probe here and the black probe here. And I get 295.4 millivolts. 295 point, I'll say 295 millivolts. So the other concept is that when I want to take a difference between two locations, this location and this location, what will I measure here? If this, what is this value here? 298 millivolts. It will be what? Yep, it will be the voltage across this resistor. And from the values I measured, what will that be? 3 millivolts. And how did you get that? Correct, the differences. So it's whatever is on the one side, subtract off the other side. So in this case, it's 298 minus 295. So the plus side, I put that probe, and now I'm comparing it instead of from ground, I'm comparing it across the resistor. Sorry, all these are coming off. Oh, these clips are not very easy to work with. There we go. Okay. And yes, I do measure 3 millivolts there. So across this resistor, I've taken the voltage that I have at the positive side and I subtract off the voltage I have on the negative side across that resistor. That is the voltage difference. And so whenever you see a voltage difference, if you don't see a difference and you see just a node, that's meaning that I'm going to be at, for example, we had it here, which was here, and that's always going to be compared to ground. So in anywhere in a circuit, a node is compared to ground, unless you see the plus side and the negative side, which in this case, we had the plus on this side of the resistor and the minus on the other. So then it's the differences of whatever voltages are there. Does that make sense? Okay, so those three concepts, make sure that you do understand. Okay, did this help demo? Okay, seeing yes. Okay, good. All right, so those are very important concepts to make sure you do understand. Because when you now see a circuit, hopefully now you'll think about this demo and be like, oh, what did that mean? And so it's like those different voltages. Let me share. All right, so these are lecture 8 notes, if you do want to grab them offline again. So I just did the demo with the floating wire. That node understanding, meaning that wherever you have a node, it is a plus there in comparison to ground. And then the voltage along the same wire and the voltage difference. So if those aren't very clear still, I'm going to put up some other, resource material again for this section for those concepts. So do make sure you understand those concepts because again, you're going to see them again and again. All right, anything as far as questions about those concepts before I move on? Okay, so for you guys that understood that before, great. Hopefully that was just a really quick review. Those that maybe didn't and were a little iffier, hopefully that feels better now. Okay. So I'm going to go over a little bit of an alternate method to do the partial fraction expansion for repeated roots in particular. I did want to back up. Somebody asked me, why this works, and I didn't have a good answer. So I wanted to come up with something I could explain really quickly instead of dwelling on that. So I thought this was an easier way to understand that. So this original equation, notice that you have e to the minus 6s in there. So whenever you see that, you're going to pull that out because all you know that means is that it does a time shift in the time domain. So whenever you see that e in the s or in the s domain, you're going to just separate that out from the actual one you're going to manipulate to get to a table form. And so I just take that part out, and then I'm going to be looking at partial fraction expansion of the rest of the equation itself. And so this equation here is going to equal the same equation, except for without that e to the minus 6s on the top. So we have, this is equal to the ABC of that partial fraction expansion. And now when we're looking at solving for A, when we multiply it, we are multiplying both sides. And so when I bring it in for the A, it's going to cancel out. For this one, it's going to be the s plus 2 on the top. And then the C is also going to be the s plus 2 on the top. So then you can either say let s equals the minus 2. And then when you put that in, the minus 2 plus 2, this becomes 0. And so the C component also becomes 0. So that's why I was saying you can basically ignore those because they really go to 0 when you've cross multiplied those both sides by s plus 2. And so now you just have a plus 0 plus 0. So the a is the only thing left. And then you plug in minus 2 into s over here. And so this leaves with minus 10 minus 2. So plus 20 over 20. Wait, plus minus. So that will still be a minus. And so you're left with minus 1, which is what we got before. So hopefully this makes more sense. And then the same thing, with B, when you plug this in and let either the limit of s goes to minus j or just let s equal minus 4j. When you plug that in here, it's minus 4j plus 4j. So this component goes to 0. These cancel, so you're left with just B. And then this also goes to 0. So the C component goes to 0. So you're left with just B, and then you plug in minus 4J where the S is. And then from before, we found that that was e to the minus J90. So see the previous solution for that. So hopefully this makes a little bit more sense about this decomposition. We're not skipping steps, but we're just, because those other components have the term go to 0, we can ignore them. So that's why that was working. All right. The other thing was with repeated roots, there's one other way you can do it instead of taking all the derivatives. So if you don't like to take the derivatives, the other way you're going to do that is by first, you're going to do the same thing where you find the C, which is going to be taking S plus 2 cubed multiplied by and then that will equal C because the A and B components terms will go to 0. Here, I'll write it out again quickly. And then we're going to evaluate this at minus 2. So 4 times minus 2 squared minus 15s minus 10. And then these terms go to 0 because minus 2 plus 2 equals 0. So this ends up giving us a value of C is 36. So instead of taking the derivatives, you can just pick some, it can be any number that you haven't used for S. So in this case, we could use S is 0, S is 1, S is minus 1, any of those. We just need 2 of them because we have 2 unknowns of A and B. So for example, let me say let S equal 0. And then as I multiply, this is going to be 4 times 0 minus 15 times 0 minus 10. And then as I multiply this, I'm going to have A times S plus 2 squared, so 0 plus 2 squared, plus B times 0 plus 2. Now I know C is 36. So I plug in those values of known, and I have an equation with A and B. So these are 0. And I get minus 10 equals A times 4 plus 2B plus 36. And then I can pick another S value, and 1 is an easy number, so just S equals 1. And again, so here I'm just using the same equation, but I'm letting S be a different value. So at 1, this is going to be 1 squared minus 15 times 1 minus 10. And then A times 1 plus 2 squared plus B 1 plus 2 plus 36. And 4 minus 15 minus 10. 9A plus 3B plus 36. From here, I'm going to solve for one of them. So I'm going to solve 2B, looks easier to solve. So I'm going to leave 2B. Change colors. 2B is equal to a minus 36 minus 10 minus 4A. All right, so minus, yeah. And so B is going to be minus 23 minus 2A. So then I can plug that in for this one. Uh, 20, what is that? 25 minus 4, 21. So that leaves me with 3A is equal to minus 21 plus 3 times 23 minus 36. Why that stopped? There it goes again. So then this leaves 3A is equal to 12. So I get A is equal to 4. And then B is going to be minus 23 minus 8, which is a negative 31. So these were the values that we had before. I just like the derivatives because I think it goes faster. So whichever way you want to do it, they both solve the system. Just depends on which one you like better. Sharing is not working. All right, questions on that? Hopefully you understand that there's another method you can use. So whichever one you're comfortable with. Okay. All right, so today we're moving on to solving actual circuits. So review is that we've gone over this before, but remember that each of these components, when you plug them into the S domain, they may have an initial condition on them. And so you have to solve the circuit first for that right before t equals 0, whatever that occurrence is. And you're going to solve the circuit for the voltage and the currents in the inductor and the voltage in the capacitor. So those values are what is going to give you those initial conditions. So for the inductor, you're going to get this IL0. And then depending on which form you want, whether it's in series or in the parallel form, again, this will just depend on your circuit and which one looks easier for you to solve. And then for the capacitor, you're going to find the VC0 minus. And then you're going to plug this in, redraw the circuit with these components in them, and then analyze that circuit using KVL, usually node voltage, because I like node voltage. And then solve it for whatever variable now you want in that circuit, which makes it nice to not have to do the derivatives also if you're finding one and then taking the derivative of the other. So a summary of the steps: transform into the S domain. You need to know those initial values first, so that's one extra step. And then use KVL, KCL, node voltage to create the set of equations, solve for unknowns with the S variable, manipulate that solution using partial fraction expansion or whatever else to get to something that looks like a similar form on the table, and then use that table to translate back, unless you want to do the whole integration, but usually we just use the tables. So questions? Any questions?
Quick question. Is this posted on Canvas yet?
Online, were you guys able to see lecture? Do you guys get lecture 8 notes? They're not posted. Sorry. I thought I posted them last night. All right, let me post these really quick so you don't have to draw these all the time. Yeah, it did not. Okay, try refreshing your pages for the notes and then see if you get them now. They should be on there. Just make sure to refresh your page. Those showing up for you guys that have computers in here? Okay, great. Sorry about that. Thanks for calling my attention to that online. All right. Okay, so hopefully now you have the lecture notes, so this should be on there now. All right, so we're gonna look at this, determine IL of t for t greater than or equal to 0, given that R is 4, 1, and C is this value. All right, so what do we have here for the source? Just a DC voltage, right? It's going to be constantly 7. So the initial condition will be what when the circuit, when that switch is where? So it'll be closed at 0. So if we're looking at this and it's closed, we need to get the initial conditions first. So the initial condition for the voltage and the initial condition for IL. So VC of 0 minus will be what when the circuit is closed? It will be 0. And IL of 0 minus will be 7/4, correct? So 7 volts over R. Remember, if you have a, let's redraw it really quick, I guess. Okay, so for the initial conditions, this will be an open and this will be a wire. And this will be closed. And we're getting IL of 0 minus and VC of 0 minus there. And so hopefully you can see that IL of 0 minus is also going to be IL of 0 minus will be there too. So 7 over R, which is 4. So these are our initial conditions. So now we're going to replace these. And the circuit is going to be now open. So what form do you think is going to be the easiest as far as parallel form or series form here? Okay, I would pick series also. I think that looks easier. This is going to be open, so I'm just going to kind of remove it there. So looking at these, I'm going to pick this one. And the capacitor one in series. Okay. So then the values. Oh, I guess they're on there. Okay. So here we have now. All right, so that's how they hook in, and then the values themselves, we have 1/SC. And then VC0 was 0, so what happens with that one? It's just a wire. So with this equal to 0, it becomes a wire. And then we have L times IL of 0 minus. So values, C was 0.5, so this is 1/0.5S. And then this is, L is 1, so this is just gonna be S. And then L of 1 times IL of 0 minus is gonna be 7/4 amps. So those will be our values. So this will be 2/S. And then how do we translate R? It's just the same, correct? Just R. I think that value was 4, wasn't it? Yep, 4. And then what do we do with the 7? Correct. Remember, U of T transforms into 1/S. So this will be 7/S. So that would be the source. And now we want to solve, what did we want to solve for? IL of T. So IL of T is here. Sorry, this is going to be IL of S. So I'll make it a big S. Heavens, IL of S. Yes. Sorry, this is actually. Yeah, that's not what I wanted to do. So it's amps times henries, which actually gives you volts. So it would be 7/4 volts. Because it was 1 Henry times 7/4 amps. And that unit ends up being volts. It's what? I drew blank for a minute. Amps is volts. Somebody else know? Let's see, this is IR. Oh my goodness, IR, so volts over ohms. It is, let's see, joules over amps squared. That's not gonna help. So this becomes joules over amps. Let me get back to you on that one. Because I'm drawing a blank for a minute. Yes, it can convert, but anyway, it will convert to volts. I'll go over that next time to how it converts. Okay, so from here, how are we going to get IL of S? Uh-huh. Okay. Sounds good. So I again like to go and circle all my signs. So here's going to be plus to minus. So I'm going to have a plus 7 over S minus IL times 4 minus 2 over S times IL minus S times IL, and then a plus 7/4 equals 0. Plus, minus, 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 plus. And then I combine all of the ILs together. So this is 4 plus 2 over S plus S is equal to 7 over S plus 7 over 4. And I get IL. Oops. 2 over S plus S. So before I combine them, I'm going to make the common denominator here. So this will be 7 or 4 times 7. 4 times 7, 28, thank you. 28 over 4S plus 7S. And then I'm going to divide by 4. Well, then I'm going to combine this side. So getting an S on the bottom, this would be 4S plus 2 plus S squared over S. So now this becomes, I just wrote that, 7S over 4S. So 28 plus 7S over S divided by 4S plus 2 plus S squared over S. And that becomes 28 plus 7S over S. And then the bottom one flips. So the S goes on the top and I get 4S plus 2 plus S squared. And the S's will cancel. Yeah. Yep, I did. Thank you. 4S, 28, 4S. So, okay. So now we want to use a quadratic to solve for that S squared plus 4S plus 2. So here S is going to be a minus 4 plus or minus the square root of 16 minus 4 times 2 all over 2. Which leaves me with a minus 2 plus or minus square root of 8. Wait. I'm wrong. S squared. Yeah, I wrote that wrong. Minus. Do that again. Minus 4 plus or minus B squared minus 4. It is right. Oh. Yeah. Yeah. Okay, that is right. Minus 2 plus or minus the square root. Square root of 8 over square root of 4, so that becomes a square root of 2. So -2 plus or minus square root of 2, yes.
Where'd that 4 go that was in the denominator at 28.7?
It's still there.
Is it just not a part of your finding the roots of the past?
It's just not in that one.
You could, if you wanted to, merge that into the quadratic and then figure out past that, right? So that.
Yeah, it should,
Plus 8 plus 4s squared.
yeah, it should give you the same.
Okay.
I just left it out and then I'm gonna divide that in, just because that's the way I had my answer. So this now becomes, I'm gonna divide that up, so it becomes 7. And then 7 over 4 becomes 1.75 S. And then this is now S plus 2 plus the square root of 2, and then S plus 2 minus the square root of 2. These are all IL. And so now IL, I need an A over S plus 2 plus the square root of 2, and a B and so A here is going to be evaluated at S equals -2 minus the square root of 2. So 7 plus 1.75 times -2 minus the square root of 2. All over -2 minus the square root of 2 plus 2 minus the square root of 2. Is that right? Minus. -2, yeah, that's the -1. And so that then becomes a 0.36. And then B is when S is -2 plus the square root of 2. And that becomes 2.11. So looking at the table, how does this translate back? What form does this have? I'll just move to this one. Usually we're getting it in one of these forms, which are a little bit easier to see. So which one is that it's going to be? Yep, it's going to be one distinct real. So I have 0.36 for A, and then E to the minus T. And then this is all the U of T, and then plus 2.11 E. What's this one going to be? Like that. Or you can, change -2 minus the square root of 2 to an actual number, whatever you feel comfortable with. That would be our answer there. All right, any questions? You guys gotta try one on your own. Okay. So go ahead and try this one. So for you guys online, I'm gonna put you guys in a breakout room to work on this problem. Oh, did I do the square roots wrong? Let me just check. So the 0.36 minus 2 minus the square root of 2. So for A, the A here would be for 0.36. Wait, do I have minus 3.36?
I think she distributed the negative sign already. That's why.
So this should be a minus plus 2. Oh wait, I am. A second. So A in this case. Oops. Be minus 2 minus the square root of 2 for 0.36 and then 2.11. The A here is plus 2 minus the square root of 2. Then it's the minus plus 2 minus the square root of 2. Okay, that should be correct now. Or I can say minus of pluses. Yeah, thanks for noticing that online. Yeah. Yeah, I just had that minus sign wrong. But that was right, Sam. Okay. All right, I will put you guys in the breakout room. All right, there you guys go, and then we'll meet back up in a minute.
So when we're doing this part here, is this 2 0 plus or is that infinity?
So we're not doing, the only thing we need is the initial conditions and that we get from the 0 minus.
Okay.
And that's because the 0 minus is the same as 0 plus.
Oh,
So that's where the initial conditions are gonna stay the same. So we're just looking at VL and IL.
Okay.
Or CC and IL.
got it.
And then this is gonna describe it for all time.
Okay.
And so we just use the initial conditions only to help determine that. So when we find the rest of the equation, so this IL of T is describing the whole time after T.
Okay. Okay, that makes sense.
Does that make more sense?
Yeah, thank you.
Okay.
Maybe my answer right.
Here, so I just plugged in the F, let's see,
Oh, the A's are named.
Yeah.
I knew it's like the A's.
yes, there, so it's minus 2 minus square root 2 plus 2 plus,
Okay.
that should be, should I have another one? That should be plus square root of 2. Other error. Yeah, it should be a plus square root of 2. Oh, no, I wrote minus, no. Minus 2 minus the square root of 2 plus 2 plus square root of 2. Yeah,
Yeah,
I'll call people's attention to that one.
okay, no, that's correct, okay, that makes sense. That's 2, and that is minus 2.
Oh, wait, no, you're, sorry. These cancel and then you're left with just the 1. So it is minus.
And,
So let me,
oh,
write it
oh,
out.
oh, oh, wait,
A ends up being, oh my, 7 plus. I'm tired today. S plus 2 plus the square root of 2. S plus 2 minus the square root of 2. Okay, then I multiply it. To get A, I multiply that by S
This
plus
one, right?
2 plus the square root of 2.
yeah, and they cancel out,
This one
right?
cancels, and then
Yeah.
you're left with the minus. yeah.
To this one.
Yep.
Okay.
And then you plug in the
Oh.
S equals minus 2 minus the square root of 2.
Okay, perfect. I was like, okay,
All right, I did write it right.
okay.
Thank
I got a question. So when you see in the final that the inductor and the capacitor, they are in series, I use this sequence in series.
Yeah.
If they are in parallel, I use the other
parallel.
one. Okay. perfect.
Yeah.
Being that we're at 9:20, I just wanted to ask, is this kind of the right direction for that circuit?
Okay, so I forgot what it was.
Okay,
It was,
that one.
yeah, open,
I treated it.
open first, yeah.
Yeah, and you gave us the initial value, so, and because this is an open circuit and that's the only voltage source, your IL of 0 is gonna be 0 amps.
Okay,
So
yeah,
basically, when I put them in parallel, it becomes a straight line.
I would put those in parallel.
And these nodes, this plus minus for the capacitor in parallel is for voltage, I'm assuming, but current is different, so the current is gonna flow here to there.
Yeah,
So that like, so positive direction current here is this way.
so, let's see, you did IS,
Which was just, this value here. C capacitance times the voltage at 0 minus 0.5 times 12.
so this ends up being 6 amps in here,
Yeah.
and you did IL. Is IS R,
Basically, I've said that the current splits, since you treat an SL like this.
there's current in this branch too,
Okay,
so you're gonna have
3 branches.
3 branches.
Okay,
yeah.
as soon as you started moving your finger, I was like, I feel like I might be mixing that.
So I would do like, again, I love node voltage, so I just do node voltage, find the voltage there.
And then I,
and do
yeah, that
V
would
over-
actually go on.
V over that SL would
Okay.
be how I do it.
And then question about the, when there's that e to the negative, like s in the numerator,
Uh-huh.
so what, like, is it because it's a time shift that it gets taken out? Like
Yeah.
mathematically, I know, like, figured out, I got the quiz wrong, so I figured out it doesn't work out mathematically, but I was curious conceptually, why does it have to come out? And I guess that's because it's a time shift.
Yeah,
So,
it's just a time shift.
okay,
And so it's only, yeah, it's representing that time shift in the S domain, so you
Yeah.
have to recognize that.
okay,
And that's why then you separate it out from the equation.
okay. So essentially, it's like an appendix kind of, it's like, here's the main thing,
Uh-huh.
but then because of this e to the negative TS, capital T, like, it's gonna shift that equation, but you need the parent equation, so to say, or the main equation first. It's kind of an order of operations in a sense.
Yeah.
Okay. all right,
Yeah.
That's super helpful. I
Okay.
appreciate it. Is everything all right?
Yeah, we just, one of those mornings, yeah. Yeah.
Glad to hear it.
Thanks.
Dogs.
All right, thank you. Okay. All right, so for these, your initial condition was given. And then with that open, you're going to have IL is going to be the 0 minus. And so your circuit will look like this. You'll have a so putting the what do you call that? Image. So with 12 volts, then you're going to have 12 over S. There we go. And that was from the VC 0 minus over S from the conversion. And then, as you guys have seen, I like to have node voltage. So I would do V over R plus V minus 12 over S over 1 over SC plus LS. And then I can solve this for V. I'll leave it as an exercise to get it into the form of 12 over S squared plus S plus 4/3. And then IL is going to be V over SL. And so that just becomes 8 over S squared plus S plus 4/3. And then that becomes S plus 1/2 plus the square root of 39 over 6J. And then a minus.
Dr. Osborne, can you share the screen, please?
And then IL is going to be a B over that quantity plus the B conjugate. And you should find that B is 3.843J, and then the B conjugate will be a minus. And so remember, the J can be converted into E to the J90. And the B conjugate is going to be 3.843 E to the minus J90. So then when you change it back, it will be a 7.686 E to the minus T over 2 cosine square root of 39 over 6 T minus 90 degrees U of T. So you leave it as an exercise to go and work through, make sure you can do all these steps. Is there a question? Yes. You could do it in parallel too. If you did it in parallel, you're going to have just a little bit different equation. It would be V over R, V over 1 over SC. And I think it's a minus. Let's see. That one would be going in. So it'd be a minus C times VC of 0 minus. And then 1 over or V over SL. And then you should still be able to get the same values. So I encourage you to, as an exercise, go through and find those. Yes.
So are we just thinking, well, we're doing series in parallel, it's easier?
Yep. Yep. both of them will yield the same answer. So it's just whatever you feel looks easier to you to solve. All right, questions? Yes, sorry. Did I not do that? I'm so sorry. Sorry, guys. All right, I'll leave those up for you guys online since I did not have that on. I apologize again. Thanks for noticing that.
On the node voltage, I was just having trouble understanding why this is just LS. This is the.
Oh, it should be V over.
V over LS?
Yeah.
Okay, that makes more sense.
Oh, sorry. We're looking at that. Okay, V over LM. There we go.
Okay, yeah.
V over R, V over V minus 12 over S over 1 over SB, and then V over LS.
Yeah, okay, that makes sense. Thank you.
Yeah, thanks for catching that. Yeah. Yeah, these are very big.
Thank you.
Yeah. Okay. All right, do you guys have questions online at all?
Yes, I do have a question.
Uh-huh.
Where's this VIL equal to V over SL come from?
So this is the current. Sorry, just 1 sec. Getting feedback.
Right. Oh. Can you share the screen? Yes, please. Yes, this one. Yes, great. Thank you. Oh, the same current. Thank you.